Here's an exciting dispatch from the world of planet research. There's evidence of liquid water on Mars, and you know what that means.
It's alive! It's alive! It's alive! It's alive!
Well, let's not get ahead of ourselves, although it's true that liquids seem to be a necessary ingredient for a planet to be inhabited. So, has Mars just become more life-friendly? I'm Seth Shostak.
I'm Molly Bentley. Welcome to Big Picture Science, produced at the SETI Institute, where researchers investigate the nature and origin of life. On Big Picture Science, we give you the wide-angle view on science and technology. Now, some planets are too hot. For example, Venus is a scorching 900 degrees Fahrenheit. Some are too cold. Neptune shivers at minus 350, and some planets are just right. Well, we know which category Earth fits into. Now we're waiting to see which describes Mars, and whether evidence of liquid water beneath its surface is a game changer. In this episode, how to make a planet, how to make it habitable, and why being too hot, too cold, too anything may be relative. It's habitable forming.
Water, schmatter. We knew that Mars has water. We've known since the start of the 18th century that Mars has water. Well, frozen water anyway. Around 1720 in Italy, astronomer Giacomo Maraldi claimed that the white spots he saw at the Martian poles were ice, polar caps, the same as Earth has.
Maraldi was at least partially correct. Some of the polar ice is water ice. We know now that some is dry ice, carbon dioxide. And we've come to understand that long ago, billions of years ago, Mars had a lot of water. The red planet was once a sloshing, wet blue one. It probably had enough water to cover half of its northern hemisphere. Today, though, Mars is as dry and dusty as the most arid desert. Something happened. The water went missing.
So, where did the water on Mars go? It's a mystery. See, we ain't talking a splash of the wet stuff. This is big, big. We're talking more water than this miserable city sees when the skies open up and don't stop crying for days. An ocean of water has vanished, just like she did into the arms of the guy with a crumpled suit and crooked smile. It's the case of the missing water. A clean sneak like that don't add up, 'cause water, it can't just disappear, not into thin air.
Well, actually it can, and that is the preferred scenario about what happened to the water on Mars. Over billions of years, Mars lost most of its ocean to space. When the planet's protective magnetic field disappeared, its surface was no longer shielded from the sun's aggressive ultraviolet rays.
Water from Martian lakes or oceans evaporated, and the ultraviolet light would split up the water molecules, the H2O in the atmosphere, into oxygen and hydrogen. But hydrogen, it's lightest, and escaped into space. Scientists estimate that Mars lost more than 80% of its water this way. The oxygen, by the way, combined with iron in the soil to produce rust, which is why the red planet is a red planet. But while Martian water is locked up in the polar ice caps, it appears that some of it also seeped into the ground.
In a potentially major discovery, European scientists have announced radar evidence for liquid water on Mars. The radar instrument, MARSIS, aboard the Mars Express spacecraft, seems to have detected water about a mile beneath the surface of the planet. The European Space Agency, or ESA, published its preliminary results in the journal Science in late July 2018. One hypothesis, it's an underground lake of salty water.
If you're on the trail of alien life, you know to follow the water, because while ice is nice, it's not a great habitat. You need liquid water or liquid something to floor the accelerator of chemical interactions and to generate and support life, says Natalie Cabral, a planetary scientist at the SETI Institute. Her specialty is ancient lakes on Mars, and she summarized these exciting results from ESA.
The authors of the discovery are mentioning two hypotheses: a body of liquid water or wet sediment.
Well, how big is this area that could be a lake?
The area is fairly big. That would be 12 miles or 20 kilometers. Interestingly enough, it's about only 1 meter, 3 feet deep.
Okay, so this is something you probably not want to dive into.
Well,
Probably not deep enough to dive into.
well, it's literally very deep because it's about 1 mile below the surface, but it's not that deep enough to dive into. We are looking at a lake that's not only under the ice, but under the bedrock.
So in order to get down to it, you'd have to go through, I think it's the southern polar region of Mars, through the
Correct.
bedrock, and then you'd be able to dive into this lake.
If you really want to, yes.
Okay. Now, the other idea is that it would be wet sludge or wet sediment. Is that what you said?
Yes, wet sediment, which means, interstitial water, but still the same idea. Basically, what's happening, and you see this on Earth all the time, is that when you have a large body of ice, like a ice shelf or a glacier, and there is topography, the ice has a tendency to move and presses really hard and moves on the bedrock. And the bedrock is not smooth, right? It has some texture to it, and the friction between the ice and between the bedrock is going to generate energy, and this is going to melt the base of the glacier. And this is what's happening. So you can imagine that 4 billion years ago, melting water would have both got to the surface and flow at the surface of Mars, but also infiltrate down. So right now, the conditions are not good for surface hydrology on Mars, but definitely for infiltrations, yes, definitely.
Does it change the nature of the discovery, whether it's a lake or wet sediment, in terms of the momentousness of the discovery, that it is liquid water on Mars?
No, it doesn't. It may, from the standpoint of the reservoir itself, of the amount of water that's there, but it gives us, regardless of what it is, and if confirmed, it just identifies a sink for the missing water that we are looking. It doesn't account for all the water that's missing on Mars. We know that Mars has lost a lot of it, escaped to space early on. A lot more is probably frozen underground in ice or in permafrost. But this is giving us another reservoir, and this is a very, very important one because this one is pretty much at the base of the main hydrological cycle of Mars.
Now, this is salty water, is that right?
Yeah.
How do we know it's salty?
Because of the nature of Mars. There are salts everywhere, perchlorate everywhere, all the sediments we're finding. It has to be salty in the first place. It wouldn't need to be salty to actually be liquid where it is. To be liquid at the surface, even in a transient phase at the surface of Mars today, you need to be salty and very salty. So this is why we're talking about brines at the surface of Mars today. But where it is located, there is no need for that. It could be actually fresh water. And the reason for this is because there is this point in the subsurface of Mars where as you are going down, the temperature is going to increase. And this is due to what we call the geothermal gradient. Same thing happens on Earth. The deeper you go, the higher the temperature goes. And another thing increases. And this is the pressure of the volume of rock you have on top. We call this the lithostatic pressure. And there is a point, a specific depth, where lithostatic pressure and geothermal gradient combine to actually maintain water liquid.
An alternative is that the salt is acting along with other chemicals as a kind of antifreeze.
But it doesn't need to. I mean, at the surface of Mars, yes, you need that to have a flow. But underneath, at this depth, you absolutely do not need this to have liquid water.
Now, could there be more than one subsurface lake?
Well, if you form one, I would say, and this is from experience. I was going to make a joke relative to life on Earth, which is a strong belief that I hold that, the most difficult thing is to find one planet with life on it. And, it's hard to make it once, probably not that difficult to make it several times. It's even more true for lakes. Once you have the process by which you are driving water down, and we have this process, is basalt melting, then, lakes or pockets of water are going to form where they can, which means that everywhere that you have either a cavity, you will form a lake. And if it's interstitial sediment, wherever the texture of the sediment, which means both the size of the grain, their shape, and their nature. Wherever this is happening, then you will have water there.
Now, even though you hypothesized that there could be a lake below the surface of Mars, are you excited about this discovery? This possible discovery?
Absolutely, absolutely, at many, many levels. I would like, though, to make an important distinction. I think that this discovery does not necessarily do much to the origin of life on Mars question. On the other hand, it does a lot for the habitability potential. And here's the distinction. Life does need energy to get started, obviously. Whether you put the origin of life in the ocean or in geothermal centers on Earth, you need some sort of mechanism to provide you energy. And unless there is a magma chamber down beneath, in which case you might have the equivalent of black smokers in that lake, which would be tremendous, it is unlikely that a place like that would be extremely exciting for the beginning, for the inception of life. On the other hand, if life started on Mars a long time ago, this is definitely a place that life would like to colonize and adapt to. So this is exciting from the astrobiology from that standpoint, but the distinction is important to make.
Well, Natalie Cabral, we are going to stay in touch with you as more information comes in. Thank you for the update on the possible discovery of a lake on Mars. And can we stay in touch?
Oh, absolutely. Thank you very much, Molly.
Natalie Cabral is a planetary scientist at the SETI Institute. Well, Seth, potentially this is a big discovery in all the many discoveries that we've heard about water on Mars, but this one is in its separate category.
This is as reliable as the locusts. It seems that every 6 months that NASA announces a news conference about something big related to Mars, and it turns out to be, we found water on Mars, but that water is almost always ice. So, that isn't terribly new. But this is new. This isn't ice. If it's there, it's liquid water. So, yeah, that's a lot more exciting.
And if it is a lake of liquid water, can you describe how significant this discovery is?
Well, the thing is this. Looking at the big picture of life on Mars, if there was any life on Mars, is that it was on Mars, right? Because Mars is presumed to have been a better place for life, for starting life, getting life going, 4 billion years ago.
Wait, a better place than Earth?
Today. No, well, it may have been a better place than
Okay.
Earth. I mean, Earth is great, but, Mars may have been better at least 4 billion years ago. So maybe Mars did cook up some life 4 billion years ago. But then Mars, unlike the Earth, Mars went bad, right? Began to lose its magnetic field, its atmosphere, and all that stuff. And so the assumption is if Mars ever did produce life, it's gone now. But if there are lakes there under the surface, maybe that life was able to, get into those lakes and survive. Maybe there's life on Mars now.
Well, this is a distinction that Natalie makes between life that is living on Mars now, meaning that Mars is a place that's habitable for life, and life that got started in the lake billions of years ago.
Exactly. Habitable doesn't mean that it's going to have life. It just means that if you threw a bunch of life at it, it would probably survive. I mean, there's life, everybody knows, in nuclear reactors, right? Some bacteria.
Everybody doesn't know that.
Well, I mean, I think if you're a bacterium living in a, uranium pile, you probably know it. But yes, there are bacteria who can live in a nuclear reactor, but nobody suggests that if you just build a nuclear reactor, you're going to generate life. It's just that life is very adaptable, particularly if you're only a single-celled critter.
Well, could life live in a subsurface lake without sunlight?
Yeah, it could. I mean, we have examples here on Earth, right? If you dig a hole a mile deep right here in lovely Mountain View and pull up the muck, of course, you find bacteria in there. Maybe I shouldn't say, of course, that's actually a discovery of the last 10 or 20 years. But, no sunlight a mile deep in the dirt here. And so if the bacteria can survive down there, they could survive, presumably, in an underground lake on Mars.
What's the chemical processes they're using to survive?
Well, they usually make use of the iron. That's how they do it on Earth. And there's plenty of iron in the soil, if you can call it that, of Mars. So they might have a similar chemistry. You just need some sort of chemical reaction that releases energy from the compounds you can find wherever you're living.
And if there were bacteria in this lake on Mars, or in Mars, I should say, they would be Martians.
They would. They would. I mean, you could check their passports, but they would be Martians.
Well, Dr. Cabral has identified why liquid water on Mars would be exciting. It could mean that the planet is habitable not billions of years ago, but today. But like the idea of water on Mars, the idea of the planet's habitability isn't new either.
It's March 1784, and the famous astronomer William Herschel is addressing London's Royal Society about Mars and the possibility that the planet had an atmosphere.
It appears that this planet is not without considerable atmosphere, for besides the permanent spots on the surface, I have often noticed occasional changes of partial bright belts, and also once a darkish one. These alterations we can hardly ascribe to any other cause than the variable disposition of clouds and vapors floating in the atmosphere of the planet. Mars has a considerable but modest atmosphere, so that its inhabitants probably enjoy a situation in many respects similar to our own.
This is a guy who, shortly after the Declaration of Independence, was talking to scientists about intelligent Martians. Okay, so his idea falls into the category of historic false impressions, but he was onto something. We continue to think that Mars might support life, microbial life.
The evidence of liquid water would further encourage this idea.
Well, I do think it's an exciting possibility.
I feel a but coming on.
It does point to the need for further data analysis.
Coming up, what it will take to confirm the claimed discovery that there is a subsurface lake on Mars.
And we know you'll keep listening. After all, it's habitable forming.
On Big Picture Science.
If there is liquid water on Mars, well, that's a major find. But at the moment, the discovery still has an asterisk next to it because it needs to be confirmed.
Whether it's a lake or area of wet sediment, the evidence came from the European Space Agency's radar instrument MARSIS on the Mars Express spacecraft. The very long wavelength of the MARSIS radar allows it to penetrate the ice at the Martian southern polar cap and the rock beneath.
Just as radar will bounce off your car because your car is metallic and conducts electricity, so too will it bounce off liquid water. But ice doesn't conduct electricity, and so low-frequency radar goes right through it. NASA, of course, has had spacecraft around Mars, too. The Mars Reconnaissance Orbiter, or MRO, launched more than a dozen years ago, has its own radar instrument, SHARAD, which stands for Shallow Radar. It works at a shorter wavelength, however, so it doesn't penetrate quite so deep into the ground as MARSIS.
The European discovery needs to be confirmed, but NASA hasn't detected the underground lake with the MRO. Now, is that because the lake isn't there or because of the difference in the instruments? It's a question confronting planetary geophysicist and co-investigator on SHARAD, Jack Holt.
You're probably familiar with radar in everyday life, like police radar, where they track your car and see how fast you're going. But when you go to very long wavelengths, so the radar waves are on the orders of meters to hundreds of meters, you can actually probe down below the surface and see things to great depths. So that's how we study features in the subsurface on Mars. But it also depends greatly on the properties of the material. And it turns out that relatively pure water ice is very easy to penetrate with radar. And the South Pole polar cap of Mars is made up mostly of water ice.
So why would the radar bounce off water underneath the surface? I mean, is liquid water somehow different than ice?
Yes, as soon as water goes from a solid to a liquid phase, its electrical properties change dramatically. Frozen water is almost transparent to radar. The radar goes through it very easily. Basically, the molecules are all bound up. They're in crystalline form, but once it's liquid, those molecules can vibrate and conduct electricity, and that then acts pretty much like a mirror to the radar. If you have a body of water below ice, it shows up like a super bright signal.
But can you be sure it's water? I mean, the Europeans who made this discovery with their radar actually seem to be very cautious about claiming it's really liquid water. I mean, could it be simply a radar reflected off a layer of rock?
Well, it would have to be different somehow than the rock that's elsewhere under the south polar cap of Mars and at the North Pole, because it's a brighter reflection than we normally see. So they have to come up with an explanation, and according to the analysis they did, their best explanation was some amount of liquid water being present at that location.
The Mars Reconnaissance Orbiter, which of course is pirouetting around our little ruddy buddy up there and has been for years, it has its own radar. I think it's called SHARAD. Has it found anything similar? Has it found any underground lakes?
SHARAD is a higher frequency radar than the one they used in this study, and we have looked for water beneath the ice on both polar caps of Mars with SHARAD and have not found any evidence for that. And there's a couple of possible reasons why we wouldn't see it with SHARAD. First off, the longer wavelength of MARSIS, the radar that's on Mars Express, is on the order of 100 meters or so. So it's not very sensitive to small roughness in the subsurface. SHARAD has a wavelength of more like 10 meters in the ice, and it apparently is being scattered by some kind of rough interfaces in the south polar cap of Mars, and we can't see to the bottom very well.
So this is an instrumentation difference that may mitigate against you being able to check the Mars Express, the European result.
That's true. That being said, if there's a liquid brine at the bottom, that's about the brightest reflector that you can come up with, aside from a giant lake of metal or a sheet of metal. So if we were to see anything at the base of the ice in the south polar cap of Mars, we should see it there with SHARAD. So I think there's some question as to why we're not, and I think that warrants some further investigation.
Jack Holt, thanks so very much for speaking with us.
Thank you very much. It was my pleasure.
Jack Holt is a planetary geophysicist at the Lunar and Planetary Laboratory at the University of Arizona, and he is a co-investigator on SHARAD. Well, Seth, if I understand him correctly, if the NASA instrument does not detect the lake on Mars, that doesn't mean that the lake isn't there.
Yeah, lamentably, that's true. I mean, I asked him, how often has the SHARAD radar aimed its beam in the direction where this lake is putatively existing there under the rusty, dusty surface of Mars? And he said, well, many times, because that instrument has been orbiting the planet for a long time. And it doesn't detect the lake, but as he admits, it's not as good at getting down deep under the surface as MARSIS, because it has that shorter wavelength. And so it's a little bit marginal, and it may be that the lake is there, but, he's just not going to see it with his radar.
What will it take to confirm the initial discovery of ESA, then?
I think that's a tough call. Obviously, I think that the Europeans will try and do their experiment again. In other words, use MARSIS and examine this area again to see if they see the lake again. And beyond that, all you can hope for is new instruments, right? Maybe a new orbiter, or, in the end, really what you want to do is drill a hole.
Well, we hope that we soon resolve the question of whether or not there's a subsurface lake on Mars. But meanwhile, we've long known that the red planet may not be the only other place in the solar system that's suitable for life. Mars is a strong candidate, some would say the strongest, for habitability, but our concept of habitability is broadening.
Consider that a half dozen other worlds in our solar system may have liquid bodies, some that are underground, and at least one that's on the surface. You could sail a boat on the lakes of Saturn's big moon Titan, but those lakes are not brimming with liquid water, but liquid ethane and methane. However, that may not rule out life, because liquid natural gas, which is what that is an organic compound. That is, it's made up of carbon-based compounds, and life as we know it is made up of such things.
So NASA wants to return to Titan to more carefully study the surface beneath its thick, smoggy atmosphere.
Yeah, I mean, we always say, if you go to Titan, don't bring a match, because there's a lot of methane in the atmosphere. And, but at the same time, there's also not a ton of oxygen, so you maybe couldn't actually start a fire. But there's methane, there's butane, propane, acetylene. But all of these things as sort of liquids and gases, because it's so cold at the location of Saturn.
Okay, so liquids and gases. Now, the thing about Titan that some people may have read about is that it actually has liquid lakes. It has lakes on its surface. And, our own moon does not have lakes, liquid or otherwise. In fact, I can't think of any other moons that have lakes. How can it have lakes?
That's that was really exciting to find that out. And actually, really no other body in the solar system besides Earth has lakes or even any kind of liquid water sustained on the surface for any amount of time. Liquid, because in the case of Titan, it's not liquid water. But yeah, now we know there are clouds and rain and rivers and lakes full of liquid methane. And it's methane because at Saturn, it's 90 degrees above absolute zero. And so water is already hard as a rock. And methane is not a gas, it's a liquid.
Okay, so does that mean that it rains liquid methane?
It does rain liquid methane, and we've seen it in a couple of cases. Once with the Huygens probe, we think there are some raindrops we saw on the surface. And another time we saw with the visible camera that sees a little bit in the infrared, and it saw a whole region change in color and then sort of change back again, probably from being wet by rainfall.
So what about the really big question when it comes to Titan? I mean, it's obviously not a really attractive place for humans, right? It's called, what's the typical daytime temperature on Titan?
90 degrees above absolute zero.
Okay. Well, that sounds like it's above something, so it must be warm, but it's not warm.
It's not. So I guess it's more like minus, 250, something like that, Fahrenheit. Minus very cold.
Okay, but could there, despite these cold temperatures, because you have these liquids, you have these lakes, and you got all this carbon chemistry going on down there, I mean, what about it? What about life?
Right. I mean, Titan really is an ideal location to look for what we say is, these prebiotic processes. We have all of the chemistry that's right, and there are a lot of organics, and there is some sunlight that gets to the surface, so there's some energy that way. And then we think, impacts happen occasionally, so those would break through the water ice crust and melt it, and now you have liquid water interacting with organics, and those are kinds of the ingredients that we think of for life. So I think we maybe don't understand exactly how this could happen, but at the same time, the conditions should be right for those prebiotic and maybe biotic processes to go on Titan.
So what's the next step? I mean, are we going to send a clipper ship to Titan and have it float around in those lakes and, sort of look around for titanian tuna or something? I don't know.
Well, that was a plan for a while. Splash down in the lakes and suck up the lake water and kind of see what we could see. That opportunity has passed because the lakes are at the North Pole and the seas, and that's about headed into winter. So we won't be able to see very well or communicate with the polar regions. But instead, we have our sights set on the equator, where there are thousands and thousands of sand dunes. But the sand is not made of the kind of sand you have on Earth. Instead, it's made of organics, and it's built up into huge sand dunes. So there's a plan to send a quadcopter, or we say it's a relocatable lander, to the surface of Titan and be able to actually sample dune sand and see what it's made of. This concept is called Dragonfly, and right now it's under study, and will be under study for the rest of the year, and a new proposal will be submitted in December for this mission.
So if all goes right, you'll have a new job, as it were, within a year or two.
Yeah, exactly. I mean, a lot of us have been working for a while toward this goal of, how can we get back to Titan? How can we understand what's happening on the surface? And we can learn so much about Titan from that.
Janie Radabaugh, thank you so much for speaking with us.
Thank you for having me. It was fun.
Janie Radabaugh is a planetary scientist and professor of geology at Brigham Young University. Well, what is the bottom line? Is this moon of Saturn a possible place for life, given everything you heard?
Yeah, well, it would be interesting if we were to find any, because it would be life not as we know it. I mean, it would still be carbon-based life form, as they always said on Star Trek, but a different kind of chemistry because it didn't require water, just a liquid. The idea of the liquid, of course, is that it brings all the chemical elements together. Now, the only objection here, I mean, there are plenty of carbon-based compounds there, right? And there's been 4.5 billion years, but, and as Janie points out, it's really cold on Titan, right? Like minus 250 degrees, 290 degrees Fahrenheit. That's really cold. And what that means is that any chemistry that's happening there happens really slowly.
So you think it's the cold temperatures that are a barrier to life on Titan?
Well, I only in the sense that they slow everything down. Things happen much more slowly. And, when you talk about producing life in the first place, let alone having some sort of metabolism. I mean, you need some chemical reactions, and to start life, if it's just a matter of having lots of oceans, in this case of liquid natural gas or whatever, and they're just sort of cooking away. Well, it's cooking on a really low flame. I mean, and it may be that even 4.5 billion years, I mean, this is a guess, of course, but even 4.5 billion years is not long enough to have cooked up some reproducing molecules that we could call biology.
What do you think it's like to be on that moon under a rainstorm of methane droplets?
Yeah, well, that's really an intriguing thought. But beyond that, some research has suggested that those drops might be very, very big, so sort of unlike the raindrops you're used to.
Well, it will be interesting to see what Dragonfly learns. If the project goes forward, as she said, it's still in the idea stage right now, and NASA would have to approve it and fund it. But if Dragonfly goes forward, we might learn more about those organics in the sand dunes of Titan.
Yeah, it's a different kind of world, for sure, and one nobody had thought about 30 years ago.
Coming up, weighing the possibility of finding life outside the solar system.
And don't knock it if the discovery is of single-celled life.
I mean, you look at the Earth, and for 3 billion years, it was just basically goo. But that's still life.
But before we leave the solar system, we journey to the asteroid belt and meet orbiting bodies that almost became planets. Find out what thwarted their plan.
We're considering which worlds might be homes for alien life. It's Habitable forming on Big Picture Science. We all know the kind of daring-do involved in flying a spaceship through the asteroid belt. You'd be lucky if you and your ship survived. And we know this from the movies.
Big rocks bumping into each other, and you need Han Solo-type piloting skills to fly between them.
Sir, the possibility of successfully navigating an asteroid field is approximately 3,720 to 1.
Never tell me the odds.
But what would it look like to really fly through the asteroid belt?
To a large extent, it's empty. It would just look like big outer space with few objects around.
But hang on, that second scenario is no less thrilling. Why? Because we've actually done it, and that guy helped us do it. Mark Raymond, the mission director for the Dawn spacecraft, and his team plotted the spacecraft's trajectory through the asteroid belt so that it did not graze a single asteroid. Although, from the sounds of it, that's not that hard to do. At any rate, we're grateful because with the spacecraft instrumentation intact, we've been able to learn more about these orbiting rocks, these asteroids.
Or should we call them almost planets? Missed it by that much planets. Indeed, when they were first spotted in the beginning of the 19th century, the objects Ceres and Vesta were thought to be planets. It wasn't until 2 generations later that astronomers decided they needed different terminology, but some astronomers still call Ceres a dwarf planet.
And that makes sense, since asteroids are really unassembled planets. These are the seeds from which planets are made, and we are learning more about that process thanks to Dawn, as the spacecraft prepares to wind up its 11-year mission.
One thing it's done is to confirm that asteroids contain a lot of water. And as NASA says, follow the water when you're looking for life. We caught up with Dr. Raymond at a recent conference.
Okay, now, as a U.S. taxpayer, I paid for this mission to these 2 rocks between Mars and Jupiter. What was in it for me? What was it that we wanted to learn?
Well, first of all, as a U.S. taxpayer, you personally contributed, I happen to know, about $1.50 for this mission. And so you got 2 worlds for that price, or 75 cents per world. And what we're hoping to learn about is these large alien worlds. Vesta and Ceres both probably were in the process of growing to become full-size planets early in the solar system history when their growth was cut off. And so They preserve the record of the conditions and processes that were in play when planets were forming. And I should also point out, people tend to think of asteroids as these chunks of rock the size of buildings or mountains. But these two places are big. Vesta is 350 miles in diameter at the equator. Ceres is nearly 600 miles. So these are big places.
They wouldn't fit between Washington and Boston, actually, the larger.
They wouldn't, and I'm not sure you would want them there anyway.
It would really increase the traffic. Well, okay, so they were planets in the making that didn't get made. Now, something stunted their growth, and when I was a kid, my mother always told me, don't drink coffee. That'll stunt their growth. What stunted the growth of these guys?
Well, my mother told me the same thing, but I don't have a good excuse for why I'm so short, because I never did drink coffee. But what probably stunted their growth is the gravitational influence of Jupiter. So the planets formed by the swirling cloud of dust and gas that was surrounding the early sun, and particles would hit and stick together and gradually grow larger and larger and larger, forming rocks and eventually planets. But when Jupiter formed, its gravity interrupted this process, stirred the material up, ejected some of it, and increased the velocity of collisions so much that instead of particles sticking together, when they hit, they would actually collide and be more destructive. And so it's likely that it was the interference of Jupiter that prevented Vesta and Ceres from growing nearby to become larger bodies.
So the Dawn mission visited both of these unformed planets, but they are round. I mean, they're balls of something. Are they rock? Are they ice? What are they?
Well, in fact, they do look planet-like, and Vesta is in many ways like the terrestrial planets, one of which is right underneath our feet. It's mostly rock, and it has a dense iron-nickel core surrounded by a mantle, surrounded by a crust. It's like a mini planet. Ceres, just a little farther from the sun, has a substantial inventory of water. In fact, something like a quarter of its mass is ice. And it also has rock and salt and other chemicals as well.
So would you call these asteroids now? I mean, what do we call them?
Well, some people call them asteroids simply by virtue of the fact that they're in the main asteroid belt. Vesta is often called a protoplanet, again because of its history of growing to become a planet. And Ceres is classified as a dwarf planet, just as Pluto is. It happens to be the first dwarf planet that was discovered because it was known 129 years before Pluto. So you and I presume most of your listeners, grew up just during this narrow window in human history after Ceres was no longer called a planet, while Pluto was still called a planet, and of course now they're both called dwarf planets.
I see, but they don't seem to care.
They don't, but a lot of people here on Earth sure do. There's still a question of how could we have been so inconsiderate? Why is Earth such an interplanetary bully? Why didn't we consider Pluto's feelings in the matter when we demoted it to be a dwarf planet?
And the answer to that is?
I guess because we're an interplanetary bully.
Okay, so how close did the Dawn mission actually get to these worlds? I mean, they're hundreds of miles across. Did it get within hundreds of miles?
It did, and in fact, prior to June of 2018, Dawn's closest distance to Ceres was 240 miles. So that's the same orbital altitude as the International Space Station above Earth. However, just in June, we flew Dawn to an elliptical orbit where once every 27 hours, it dips down to only 22 miles. That's only 3 times higher above the ground than you are when you travel cross-country in a jet. So we're really getting some spectacular views.
All right, well, give me an idea of what you see when you're that close to these things.
Well, one of the things that I think is pretty neat is we can see a lot of boulders on the ground and indeed on crater walls. So on the walls, we can see boulders that have slid partway down and haven't yet fully succumbed to the influence of the Sirian gravity. Also, Ceres has some strange, bright features that are just, to me, mesmerizingly beautiful and just captivating in their brightness, which we now understand to be salt flats. That is, Ceres has underground salt water. In some cases, this water made its way to the surface, and the cold environment there, it froze and then sublimated, that is, transformed from being a solid to a gas. and left the salt behind, and we can see details of the deposition of this bright salty material on the much darker ground on Ceres, and this undoubtedly will give us more information about how this material really got there.
Mark Raymond, thanks so very much for talking with us.
Thank you, Seth. It's always a pleasure to see you and to talk to you and your listeners.
Mark Raymond is the mission director on Dawn. And by the way, when the spacecraft stops communicating with Earth sometime in the fall of 2018 and its mission is effectively over, it will remain in orbit around Ceres.
You know, talking about water in connection with life, it might be worth mentioning that one very plausible and popular theory about how we got the oceans here on Earth is that that's actually asteroid juice, or a lot of it. We heard that, maybe 1/3, 1/4 of all the mass of these asteroids that Mark has been studying are water. And it could be that 4.5 billion years ago, a lot of these asteroids got pretty close to the Earth, slammed into it, and delivered all the water that we now call the oceans.
Now, does that mean that the water in these asteroids could contain life? Could it be habitable?
Well, I think it's a long shot because, after all, it's kind of buried water and all that. But all the ingredients are there. They just need a little bit of energy to get life started. And maybe billions of years ago, when these rocks were a lot hotter, maybe there was enough energy. I wouldn't rule it out, but there's no evidence so far. And so becoming a planet is not easy, no matter how keen you are to try. And yet we've discovered a lot of bodies that made it to planet status, not just those in our solar system, but many, many more beyond it. What does that say about the likelihood that they'll have the conditions needed for life?
Well, the answer is becoming more often, it depends. Whether we're talking about moons, planets, or other bodies, our definition of what might be habitable has broadened. You might not even need water if another liquid like that in Titan's methane and ethane lakes is available. So, for the last word on the big picture of habitability and whether Earth is special, we talked to astronomer Phil Plait at the Space Fest conference in Tucson, Arizona.
Phil, we're here at Space Fest in lovely, sizzling Tucson, Arizona, and you gave a presentation here addressing the question of whether Earth is special. Is that an easy question to answer? I mean, obviously, I think it's pretty special.
Yeah, well, I think it's special too, but I'm biased, right? I'm human. I evolved here on this planet. I'm the tail end of 4 billion years of evolution. We all are. But honestly, we're finding a lot of planets, and there are some number of planets in our solar system, 8 or 9, however you want to count them. And the Earth is the only one that we know of that has life on it, and it has the temperature and the chemistry and the liquid water on its surface. In that case, you could say Earth is special. But as you start to look at more conditions, if you need water, there are lots of moons of giant planets, and they have water under their surface. Maybe you don't need water. There's Titan, the moon of Saturn, that has liquid methane on its surface. That could be supporting life. Mars used to be habitable billions of years ago, and now it isn't. So you have to look at a certain time range. The Earth may not be habitable in 100 years, 200 years, who knows? We're changing it. So yeah, the Earth is special. There may be lots of planets like it in the galaxy, but probably only one that is just like ours.
Okay, so that sounds like you're saying, look, the neighborhood that you live in, for example, I'm sure it's special, right? You got special neighbors. I don't know, maybe you got better maintenance or something near a shopping center, whatever. It's special, but it's not the only place you could live. So if you're defining a planet as being attractive on the basis of its suitability for life, then maybe Earth isn't all that special.
Yeah, I think that's pretty much it. And at the risk of sounding pandering, I was at Seth's talk earlier today, audience, and you said a really interesting thing. You said that we are special but not unique. And I thought that's great, because if you deal out 5 cards of a poker hand, and it could be any 5 cards, any 5 cards you get, that's unique, but it may not be special. It may be garbage, it may be 2, 4, 6, 8 of different suits. That's not very special, but it is unique. It's the only hand like that. It's kind of the same with us. We're unique in that the conditions that we have here on Earth aren't replicated anywhere else in the galaxy precisely. But we may not be special in that you don't need those exact parameters. You could have a little more carbon in your planet. It could be a little bit cooler, something like that, stronger magnetic field. So yeah, we're unique, but there may be lots of other planets like us within the range of habitability that we expect to have liquid water on the surface or just conditions for life.
So does this speak well to the idea of a Goldilocks zone, a zone of habitability around any given star?
Oh, he says with malice aforethought. We have this idea that you have to be a certain distance from a star, and we call that the habitable zone. And that is, if you're too close to the star, it's too hot, and if you're too far from the star, it's too cold. And so this reflects the fable of Goldilocks. But of course, it's not really Goldilocks, it's the baby bear zone, because the baby bear was just right. It wasn't too hot, it wasn't too cold. So really, it should be the baby bear zone, but I will defer to other astronomers who call it the Goldilocks zone. This is a good concept. It's a nice way of guiding your thinking and saying, well, if you're at the right temperature range, you can have liquid water on the surface. But, it depends on your atmosphere. Venus has an atmosphere, and it's inside the Goldilocks zone, but it's way too hot. Mars doesn't have an atmosphere. It's also inside the habitable zone of the sun. It's way too cold. And in that case, it's very useful. Just don't let it box you in. There's a lot of stuff going on out there that we may not yet understand.
So given that there are more planets out there than there are stars, and that in any given solar system, say our solar system, there might be a half a dozen, maybe even a dozen places where you could have biology, if your definition of what makes a good planet is, well, it has some life, well, then there are going to be a lot of good worlds out there.
Oh, I agree. And we just don't know yet. I mean, you look at Jupiter, it's 5 times the distance from the sun that the Earth is. It's really cold there. Saturn is even farther out. It's really cold there. Typically on the surface of a moon of Saturn, it's so cold that water ice is as hard as granite. And yet, these have liquid water in their interiors. They're heated by the gravity of their host planets. There are lots of moons around Jupiter, lots of moons around Saturn, Uranus, Neptune, even these Kuiper Belt objects out past Neptune, of which Pluto is one of the biggest examples. And so you could have liquid water all over the place. The more we study these objects, the more we realize, yeah, there could be a lot of places where we hadn't traditionally thought of as being habitable for well, not necessarily humans, but just life, whatever that might be, amoeba or whatever. I'm very hopeful. I think we'll find life in a lot of places that we look in the galaxy. I think it's going to be single-celled. I mean, you look at the Earth, and for 3 billion years, it was just basically goo floating in the ocean, yeast and algae and stinky stuff like that. We may find a lot of that, but that's still life.
How about just taking it from another tack, the opposite tack, that maybe Earth is special in being actually not quite up to snuff? Maybe most planets where there's complex life are actually better than Earth. I mean, there's a lot of things you could complain about here on Earth. A lot of it isn't very useful. Could it be that our planet is actually suboptimal?
Oh, I hadn't really thought of that. That's a good question. It turns out that you need a certain percentage of rubidium in your crust to be a member of the galactic elite. And there's, a few thousand planets out there, and they look at us and we're like, oh dear, Earth, they're very rubidium poor. We should really not discuss this with them. A lot of the Earth is uninhabitable for us. It's ocean. I live in Colorado, where if you get up too much higher, it gets hard to breathe. I have people who can't visit me because they have a hard time breathing where I live.
At least that's what they say.
Yeah, that's what they say. That's true. And who knows? Maybe it's just because I haven't done my laundry in a while and the atmosphere in my house isn't that great. Yeah, maybe we think of the Earth as being this rich, wonderful treasure chest of life-supporting physics, but in fact it may be that we find these other planets and we have a paucity of these things. That's a nice little way of looking at it. And it's a good way of looking at it, because the more we change our point of view, the more we think, do things have to be this way? The bigger our vision becomes, and the more we're likely to see out there when we look for life.
Phil Plait, thanks so much for speaking with me.
Seth, it is always a pleasure.
Phil Plait is an astronomer, and he writes the Bad Astronomy blog.
Okay, as we've heard in this show, the discovery of a possible underground lake on Mars has once again given hope to those who are expecting, or hoping at least, for Martians. Maybe if there were ever Martians on the red planet, they were able to retreat to this lake, maybe other lakes, and survive 4.5 billion years. So I'm all for sending a drilling team to Mars and checking it out. But meanwhile, we've noted how the concept of habitability, once so simple, is much less simple now. Moons that are in the outer parts of the solar system, places that are cold and, you might say, terrible places, these might actually be homes to biology. This is an idea that, people would have considered radical 100 years ago.
Thanks to the team members whose excellence in helping produce the show has become a matter of habit. Senior producer Gary Niederhoff and operations manager Barbara Vance.
Thanks also to financial support from Rena Shulsky-David and Sammy David, and to the William K. Bowes Jr. Foundation. Big Picture Science is produced at the SETI Institute, a nonprofit scientific and education organization whose scientists study the origin and nature of life, including the moons of the outer solar system. And a big thanks also to our listeners.
Your ears have been attuned to an episode of Big Picture Science called It's Habitable Forming. And if you want to hear more Big Picture Science episodes, well, you'll find them in our archive at bigpicturescience.org.
Hi, doll. So you're back.
I'm just here to pick up my Barlow lens.
Still with a guy with a rumpled suit?
It's a lab coat, and yes,